Okay, we are going to finish chapter 10 today about gases by talking about ideal gases. And really, when we've been talking about gases, we have been pretending that they're ideal this whole time. I'll give you a few seconds to copy down these notes. Okay, and then there's just a little bit more. Okay, so like I said, we have been pretending that these gases are ideal gases. An ideal gas is a gas whose behavior is perfectly predicted by the kinetic molecular theory that we talked about in section 1.1. And if you remember when we talked about kinetic molecular theory, there were some things that we said about gases. We said that they're really tiny compared to the great distances between them. They're moving randomly with high velocities in all directions at many different speeds. And we said the particles do not interact with each other or the walls of their container, except for momentary collisions. Collisions between gas particles conserve energy, and the average kinetic energy of the gas particles is directly proportional to temperatures of the gas in Kelvin. Well, the problem is there are some problems because no gases are ideal. Just like people, there are no ideal people. Nobody is perfect, except for Jesus was perfect. And no gases are ideal or perfect because, for one thing, all molecules have volume. Kinetic molecular theory assumes that they do not have volume, but they do in fact have volume. Another problem is at low temperatures and high pressures, gases can liquefy because there are some forces and interactions between them. And there is some interaction between molecules, reducing pressures and volumes. So there are no ideal gases. So they break the rules all the time. Now, the closest we get to ideal is when we have a low molar mass. So the most ideal gas, or the closest to ideal, would be hydrogen, something like hydrogen, helium, low pressure, and high temperature. And so molar volume is actually an approximation, and there is a table in your book in section 1015 that shows that this is an approximation. Different gases do actually have different molar volumes, but they're all pretty close to 22.4, especially those ones with the lowest molar mass. So they do break the rules because they are not perfect, just like people. And so section 1016, we have the ideal gas law, PV equals nRT, which P, V, and T look familiar: pressure, volume, temperature. The new variables are N and R. N is moles, and R is the universal gas constant. And, you know, this should look really familiar, the PV and the T, because we talked about Boyle's law, Gay-Lussac's law, and it's really late, so I'm not remembering the other one, but we already talked about those laws with the PV and the T. And so those were proportions, and what we can do is when we throw in a constant, we can actually make them into an equation. And this constant has three different values that we might use. The difference in the values, notice here, is due to the pressure. Okay, so depending on what values we use in our equation, we will use a different number for the constant, but if we were to do a conversion between them, they would all be equivalent. This last one here is the metric value. And sorry I didn't give you a couple seconds to copy that down. So let's take a look at some problems using this new equation, PV equals nRT. Sorry you're having to wait for me. I forgot to get out my notes for this. Okay, so the question is, how many moles of a gas are present in a 2.4 liter sample of 1.25 atmospheres at 1.25 atmospheres of pressure and 27 degrees Celsius? So I want to know moles. I'm given volume, pressure, and temperature. And I'm going to use my new equation, PV equals nRT. So I am after N. For pressure, I'm given 1.25 atmospheres. For volume, 2.4 liters. And for temperature, 27 degrees Celsius, which I have to convert to Kelvin. So that is 300 Kelvin. Okay, back to my equation. My R value depends upon my labels here. And because I have atmospheres, liters, and Kelvin, I am going to choose the one with atmospheres, this number right here. So I am going to choose 0.0821 liters times atmospheres over moles times Kelvin. So that is my R. Now, for my equation, I am trying to find N. And I usually plug in my numbers and then move them around. But I'm going to do this one a little bit differently because that's some really long numbers and some really long labels. So I'm actually going to solve for N. And to solve for N, I have to divide both sides by RT. So my equation will become PV over RT equals N times RT over RT. These cancel out. So my equation is N equals PV over RT. So just like we solve for numbers, we can solve for variables. Now, plugging in my values. So N equals, pressure is 1.25 atmospheres. Volume, 2.4 liters. R, 0.0821. And then all of these labels. And that is important because they all cancel out. And temperature, 300K. So atmosphere, atmosphere cancels. Liters, liters cancels. Kelvin, Kelvin cancels. Now this ends up being 1 over moles, so moles actually flips up to the top. So N is, when I multiply 1.25 times 2.4 and divide that by 0.0821 times 300, I get a value of 0.12 moles. 2 significant digits because of 2 significant digits there. So that's how we do that problem. Another kind of problem we can do using this equation is we can calculate the molar mass of a gas from its mass at non-standard, whoops, I did not spell standard correctly, conditions. So go ahead and copy this problem down. Okay, so I have a 5.04 times 10 to the negative fourth kilogram sample of gas occupies 4.57 times 10 to the negative fourth cubic meters at 9.63 times 10 to the fourth pascals and 293 K. What is the molar mass of the unknown gas? So I'm going to use my ideal gas law to find the moles. So we are after N. We have PV equals nRT. We're after N. We have pressure, which is 9.63 times 10 to the fourth pascals. We have volume, which is 4.57 times 10 to the negative fourth cubic meters. And we have temperature, which is 293 K. Now our R value from my list is this one, because it has cubic meters and pascals. So R is 8.31 cubic meters times the Pascal over moles times Kelvin. Okay? Again, we solved before for N, so I'm just going to write it as N equals PV over RT because we already solved for that. So in the last one, I showed you how to do that. So when I plug in my values, N equals 9.63 times 10 to the fourth pascals times 4.57 times 10 to the negative fourth cubic meters over 8.31 times 293K, making sure that all of these cancel out. So I'm left with 1 over a mole, which 1 divided by 1 over a mole is a mole. So N ends up being 0.0181 moles. Okay. Now we're going to find the molar mass. To do this, we divide the mass of the sample in grams by the number of moles, which is N. And this is equal to the molar mass over 1 mole. So the problem with our mass is that it's not in grams, it's in kilograms, so we have to convert. So 5.04 times 10 to the negative fourth kilograms. Remember, in 1 kilogram there are 1,000 grams. So we end up multiplying that number by 1,000 and we get 0.0504 grams. So we take that number and we plug it in up here, 0.0504 grams divided by 0.0181 moles equals 27.8 grams per mole. So these are ways that equation is useful, and people have, scientists have used this equation to find molar masses. Okay, so let's go on to page 268, number 8. I'm just trying to find a paper to cover it up here. There we go. And we will, well, actually, yeah. I will not give you the answer. Let's just do it together. Oh, I need paper. Sorry, guys. It's been a long day, and it's actually almost 10 o'clock at night here, so I'm just a little tired. And so let's do page 268, number 8. So the book says, how many moles of oxygen will occupy 1 liter at a temperature of negative 118 degrees Celsius and a pressure of 49.77 atmospheres? Use the ideal gas law to solve the problem. So we know we're using the ideal gas law. So PV equals nRT. It was really funny earlier because I was saying that I was working with ideal gases, and my husband, who has not done this in lots of years, probably well over 20 years, rattled this equation right off, which was kind of funny. When I said ideal gas law, he just rattled this right off. PV equals nRT. So we are trying to find moles. Okay, and like we said earlier, we had rearranged this. N equals PV over RT. I had shown you how to already do that, so we'll just go straight there, and you're going to be allowed to use your notes on the test, so you'll be able to find a problem like this and be able to do that, or you know how to do that. So you just divide each side by RT to get N by itself. So we're given pressure, which is 49.77 atmospheres. That's pretty high pressure. That's 50 times normal atmospheric pressure. Volume is 1 liter. Temperature, we actually have a negative temperature here. So we have to convert that to Kelvin, and we get 155 Kelvin. And our R value, because it's atmospheres and liters, will be 0.0821. L atmosphere mole. Okay. So now we'll just plug these numbers in. N equals pressure volume 1, temperature, or actually R first, so 0.0821, and temperature. Now my units cancel out. I'm left with 1 divided by 1 over a mole, so that flips up. So N equals, when I multiply these numbers together and divide them by these numbers multiplied together, I get 3.91 moles. Okay, is my answer. So that is 268, number 8. I'm going to stop the video here and do the homework problems in a separate video. So I will be back.